Me again. Still the same day. We're getting a few done today, some physics ones and some maths ones. Okay, so move on to chapter 18 now in maths, which is the binomial distribution. In class earlier today we sort of did a question that was related to binomial, but we'll look at it a bit more in detail now. So binomial, which means two. So binomial, two possibilities. Two possibilities, okay, if it's spelled. Two possibilities. Okay. So, for example, a coin, head or tail. That's not this one. I was going to say a football match, win or lose, but then you say, oh, what about a draw? There are lots of different things, hit or miss. You might say with a dice, there's not two possibilities with a dice, there are six, 1, 2, 3, 4, 5 or 6, but it might be with a dice, 6 or not 6. With children, boy or girl. Maybe even that gets a bit more complicated nowadays as well. Alright, but let's not get into that. So, if I, let's start with a coin. So the probability of a head equals a half, probability of a tail equals a half. That's okay. What about if I toss a coin twice? Or toss two coins? Yeah, I mean, as long as one's not affecting the other. Alright? So, it might be that with football matches, if you've lost the first 3, then you're more likely to be losing again, or all sorts of things. But we're assuming that one outcome doesn't affect the other. When you toss a coin and get a head, it doesn't make it more likely or less likely that you're going to get a head the next time. Okay? Toss a coin twice, so we can draw a tree diagram for that. We can get a head or a tail, and then we can get a head or a tail again. So that would be head, 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 tail, tail, head, tail, tail. So probability of 2 heads equals a half times a half equals a quarter. Probability of 1 head, and therefore 1 tail, is this one, which is 2 quarters, or a half, and the probability of no heads is equal to 1 quarter as well. Alright? And if we do it 3 times, see the 8 equally likely outcomes. This would be head, head, head. This would be head, head, tail. This would be head, tail, head, head, tail, tail. Head, tail, tail. Tail, head, head. Tail, head, tail. Tail, tail, head. Tail, tail, tail. Probability of 3 heads is equal to 1 out of 8. Probability of 2 heads. Well, there's 2 heads, there's 2 heads, and there's 2 heads. So it's 3 lots of an 8, or 3 eighths. Probability of 1 head is equal to, there's 1 head, there's 1 head, there's 1 head, again it's 3 eighths. Probability of no heads is equal to 1/8. That's the only possibilities. If you toss 3 coins or toss a coin 3 times, then you can only get 3 or 2 or 1 or no heads. You can't get anything else. So those probabilities must add up to 1. 1, 3, so 8/8 adds up to 1. Alright. If I toss a coin 10 times, I don't think we've got to draw a tree diagram for that. So clearly there's a better way of doing it. I mean, for 3, then that's fine, nothing wrong with that. But if you're going to toss a coin 10 times, then you know we need to have a shortcut method. So in general, if probability of success. And what does success mean? Well, it depends, you know, what the question's asking. Success might be Bill winning, failure might be Bill not winning, but you know, success might be throwing a 6, success might be throwing a head, you know, whatever. But if probability of success is equal to P, so that's a capital P for probability, and we're normally using little p to stand for success. Therefore, probability of failure, so not success, is just 1 minus p, or sometimes q. Okay? And p plus q must equal 1. Well, of course, if it's p, then 1 minus 2. Okay. So I toss a coin 10 times. What's the probability I get 3 heads? Exactly 3 heads. All right. Probability of 3 successes. Now that might be 3 heads or not. For n trials, probability of 3 successes. Alright, let's say for 10 trials. Probability of 3 successes would be P times P times P times Q times Q times Q times Q times Q times Q. Is it 7 yet? Times Q. Okay, equals P cubed times Q to the 7th. Note that for 10 trials, those two numbers must add up to 10, but what we've worked out there is the probability that the first 3 tosses are successes, and then I have 7 failures in a row. I could have had P, P, Q, P, Q, 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 or I could have had Q, Q, P, P, you know, lots of different probabilities there. In fact, those 3 could be arranged in 10C3 ways, 10 combination 3. We did that, you know, early last year. Okay. So there are lots of ways these 3 successes can be distributed, 10C3 ways, lots of different ways. So the probability that x equals 3 is 10C3, lots of p to the power 3 times q to the power 7. Not sure if the book uses q or 1 minus p. Yeah, they just use 1 minus p, so I'll write that up for you as well. For example, in this case here, the probability of getting 2 heads, right, that would be, so out of the 3 trials, I want 3C2, lots of success squared, so a half squared times failure to the 1. They need to put the 1 there, but that just emphasises the 2 plus 1 equals 3. So 3c2 times a half squared times a half to the 1. Half squared times a half to the 1 is 1/8. 3c2 NCR equals n factorial over n minus r factorial. So 3c2 equals 3 factorial over 2 factorial, 1 factorial. It's 3 by 2 by 1 over 2 by 1, so that's just equal to 3 over 1, that's equal to 3. So we get 3 lots of 1/8 or 3/8. It's a bit tricky when you get more than 3 or so trials, so 3/8. So there we've got there, let's put up a general expression for that. In trials, the probability of success P, the probability of X successes becomes NCX, let's write that as a little x, NCX times P to the X times 1 minus P to the N minus X. Or we can write that as NCX times P to the X times Q to the N minus X. Put that whole thing in the box for you. And again, that's in your data booklet. So let's do an example of that. Surely one of these pens works. Sorry, it's getting so faint. Okay, e.g. Okay, so Conica, when she fires a bow and arrow, shots, 8 arrows. The bow at the target. Probability of hitting target. It's a pretty good shot. We'll make it 0.7. Okay. So therefore the probability of missing is 0.3. What is probability of hitting 6 times? Okay. Now, how many would we expect? So, if each one is 0.7, then the probability that she hits, she's firing 8 arrows with a probability of 0.7. 8 times 0.7 is 5.6. Clearly, she can't hit the target 5.6 times. She might hit it 5 times or 6 times. So they should be the most likely. We might work out a couple of them. The probability of hitting 6 times. Okay. So that becomes NCX 8C6 times 0.7 to the 6 times 0.3 to the power 2. 8C6, right? So you've done your Pascal's triangle before. 1, 1, 1, 1, 2, 1, 3, 3, 1, 1, 4, 6, 4, 1, 5, 10, 10, 5, 1. We're going to do the 8th row. We're running out of space. 1, 6, 15, 20, 15, 6, 1. 1, 7, 21, 35, 35, 21, 7, 1. Finally got there. 1, 8, 28, 56, 70, 56, symmetry of course, symmetrical, 28, 8 and 1. Hope that's right. Alternatively, 8c6 is 8 factorial over 6 factorial 2 factorial, which becomes 8 by 7 over 2, becomes 56 over 2, should be 28. 8c6, there's 8c0, 8c1, 2, 3, 4, 5, 6 is certainly 28. It's 28 lots of 0.7 to the 6 times 0.3 squared, whatever that is. Okay. And we can work that out for other values as well. You need to be able to do that. You need to be able to use the binomial formula by hand. And you also need to be able to use your graphing calculator. And it's pretty extraordinary what the graphing calculator can do. I would think, you have all used your graphing calculator to draw graphs. You have used your graphing calculator to make calculations. You've used your graphing calculator as a paperweight to hold notes down. I think most of you won't have used it as a probability calculator. So, pause this video, grab your graphing calculator. I've had mine plugged in here to charging up. But I think there might be something wrong with the battery, so we'll see how we go with it. Okay. Okay, are you back? Alright, so let's, so you need your graphing calculator with you. You can listen to this, but if you're not doing it yourself, then you're not going to be sure of what's happening. Okay, with your calculator, in the calculate one, go to menu. Menu, we've got actions, number, algebra, calculus, probability. Move down to probability, or you just do 5. Across we go. Factorial, permutations, combinations, random and distributions. Distributions is what we want because we're doing probability distributions. Distributions, and now look at all of these guys here. Normal PDF, normal CDF, inverse normal. That's the next exercise, we'll be using those soon. T PDF, T CDF, we won't be using that. Inverse T. X squared, it's actually chi squared PDF, chi squared CDF, inverse chi squared, F PDF, keep going, down the bottom, under 9A, F CDF, inverse F, binomial PDF, that's what we want. One below that is binomial CDF, and then geometric PDF, geometric CDF, then Poisson PDF, Poisson CDF, and then back to the top. Okay. So there is a lot there. It's under D for binomial PDF. PDF, probability distribution function. Probability distribution function. Binomial CDF, you'll be using that as well, and that's binomial cumulative distribution function. We'll worry about that in a moment. So at the moment we want binomial PDF. Okay. Up comes a little box, number of trials. Let's go back to this one here with the 2 heads, the one we worked out there. We know what the answer is. Alright? So I toss a coin 3 times, what's the probability of getting 2 heads? So the number of trials is 3. Put that in. What's the probability of success? 0.5. X value. I want to know what's the probability of getting 2 heads? Alright. Okay, and enter that. Out comes our answer, binomial PDF, and it gives us, in the solution, in the answer, it gives us sometimes it's a bit hard to remember which order things go in. And you know, I think this one's pretty straightforward, but you know, so you've got to be careful. I mean, it's 3 trials, and yeah, I mean, they lead you into it in the box beforehand. How many trials altogether? What's the probability of success? How many are you worried about? How many successes do you want to find out about? 3 altogether. 0.5 is the success, probability of 2, 0.375, 3/8. Well, that's what we've got. Of course, it's 2 3/8. All right. Let's try this one. Okay. So binomial PDF. You know, so I mean, we could work this one out. Nothing wrong with that. But it's a lot quicker if I just say number of trials, 8. Probability of success with Konica shooting, 0.7. The X value, 6 times. Down we come, and enter, and it gives us 0.296475. Hopefully that's what this turned out to be, 0.296475. Now, of course, you're giving your answers correct to 3 significant figures, 3 decimal places. So in this case, 0.296. Just. If you are then going on with this in a further part of that question, for example, you know, every day Konica has 8 shots at this for a week. Each day the probability that she gets is 0.296. For the week, and then it becomes a binomial on a binomial. For the week, what's the probability that, you know, on 4 days of the week, she ends up hitting 6 times? So then you're using that number, but use the rest of it as well. So round off your answer to 3 significant figures, but use more than 3 significant figures in subsequent calculations. All right, so okay, so probability of 6 worked out was 0.296. What about the probability of 7? What's the probability that Konica gets, gets 7 successes? It's presumably less, you know. So, you know, probability of 6 is reasonably high. Let's actually find probability of 5 as well. Probability of 7, probability of 8. Okay. So see if you can do that. Let's have a go at that together. And I'm sure you're a lot quicker at this than I am. That's all right. Okay, so I want 8 trials. I'll do the first one. 5 successes. Oops. 0.5, 0.7. Probability of 5 successes. I think it'll be quite similar to the other one, 0.254. Probability of 7 successes. We've got 8 trials. 0.7, probability of getting 7, a bit smaller, 198. And the probability of Konica getting 8 out of 8. It's got to be getting pretty small now, doesn't it? The probability that, you know, she gets it each time is 0.7. The probability that she gets it 8 out of 8 has got to be getting pretty small. So I'm thinking 0.1. We're just looking at the pattern there. It's going up. You know, so the probability she doesn't get it at all is low. It's high around there. So, you know, there's 5, there's 6, there's 7, there's 8. So, you know, we're expecting that to go down. So probability of 8. How about I stop talking and do this? Probability distributions, binomial PDF, 8 successes, 0.0576. So 0.058. I'm going to write that as. Alright, good. Now, if the question had been, so she's firing 8 arrows, what's the probability that she hits the target more often than she doesn't? That means that she gets out of 4. What's the probability? Yeah, so let's say she hits the target more than 4 times. So more than she misses. At 4, you couldn't say that she's hit it more than she's missed it. She's hit it at the same time. So what's the probability that she hits the target more often than she misses it? Okay. So that would be 5, 6, 7, 8. We can add those together. Let's add them. I know that a couple of them we rounded down. There was 0.254. That was 0.2964, that was 0.254 something. This is 1.197 something and 0.057 something. So, yeah, when we add them together, we should be pretty close to the right one there. Let's add them together. 10, 18, 26, 7, 16, 25, 30, and 3, 4, 6, 8. 2.806. Okay, that seems reasonable. Well, a calculator does that for us as well. That's what the CDF is all about. So, try now the binomial CDF. Alright, so we're going to get menu, probability, distributions, binomial CDF. Number of trials, 8 trials. Probability of success, 0.7. So far, exactly the same. Now, lower bound. Alright, well I want to go from 5 to 8 inclusive. So my lower bound is 5, my upper bound is 8, 0.8058, or 0.806. So the cumulative is adding them together for you. Okay? Very different distributions. And so you need to be careful that you're using the one that you want to be using. Are you wanting to find the probability of a particular thing happening, or are you wanting to find the probability of a range of things happening? Okay. That's enough for now. I think that's 18C. You've got lots and lots to do from that. And the next one we move on to is normal, which is even more interesting. If that was possible, it is.